We're very excited to host in this panel with three fantastic speakers alongside me, which we will be introducing very shortly. I will let's say to warm up. I will introduce myself, and then I will let Martin from Airbus, Danny from Rolls-Royce Submarines, and Daniel from Nissan introduce themselves. So my background, I'm an aerospace engineer. I have a background in space propulsion, optimization, materials, and simulation. So I've done a few different things in my engineering life. Prior to I worked at ToffeeX, and prior to ToffeeX, I was at ANSYS, and prior to that, I was at a company called Granted Design, which was a spin-off of Cambridge University that was acquired then by ANSYS. And I joined ToffeeX roughly over a year ago. And the main reason I did fall in love with its incredible thermal fluid topology optimization software. Now, for those of you that don't know, I imagine most of you will, but for those of you that don't, ToffeeX spun out a few years back from Imperial College London, thanks to I would say, the genius of our CEO and founder, Marco Pietropaoli, which was at the time a PhD student of Professor Francesco Montomoli at Imperial College. Today, we are roughly 30 people, and we work with a remarkable set of OEMs and tier 1 suppliers that are our customers. Now, my role within this company, I work alongside Marco, the CEO, and my role is really to drive the success of ToffeeX, let's say advocating for new engineering design paradigms, and by, let's say, promoting the adoption of innovative generative topology optimization for thermal fluid applications. And I believe that this will ultimately push the boundaries of what's possible and help engineering enterprises create innovative products faster. Over to you. Maybe I'll start with Martin.
Hi, everyone. I hope you can hear me. I'm Dr. Martin Muir from Airbus Central Research and Technology. I'm also a part-time employee of Airbus Blue Sky. So in my role, we look at upstream technologies and research trends, trying to bring those technologies, those emerging methods, etc., into Airbus and into the majority of our business units, commercial, defense, helicopters, etc. I've been doing this for about 15 years, and I've worked on everything from deep range spacecraft all the way to submersible products. So Danny and I have something in common there. Looking at various types of modeling simulation technologies applied through additive manufacturing, advanced simulation, advanced computing methods, etc. And today we'll hopefully be talking a little bit about my view on this from a commercial aircraft standpoint.
Thank you, Martin. Danny?
Good morning, my name's Danny Duda. I work for Rolls-Royce Submarines, and I have done for the last 17 years. Rolls-Royce Submarines has been supporting the Royal Navy's fleet of nuclear submarines ever since there has been one, so that's for about 60 years. And my career so far, after a degree in mostly mechanical engineering, I've been involved in design, justification, introduction to manufacture, and support in service for our fairly complex array of products that I hope to be able to talk about some of that experience today. Thank you.
Thank you, Daniel. And Daniel from Japan.
Hi everybody. I'm Daniel Mack. I work at Nissan. I'm based in Japan, but I went to Imperial College, same as the ToffeeX people. So I have a background in mechanical engineering. My main area of research at the moment is the application and design of additive manufacturing, additive manufactured components. So we look at design, processes, material, and also the business case to actually apply it on a product.
Thank you, Daniel. So for the audience, this is going to be a conversation on the future of engineering design. We don't have slides. It's going to be very much a workflow that will lead us to, let's say to a point that is not prepared. So it will depend a little bit on what we discuss. Now, this morning while I was getting into the ToffeeX office, I was reading something that I thought was interesting, and I thought I'm going to read it before starting to discuss key trends in key technology trends in engineering, and hopefully it will help us. It will serve as a springboard for this discussion. So I was reading these letters to the stakeholders from the CEO of Synopsys, Asim Ghazi, and there is a passage that I'm going to summarize, which I thought was pretty good. I think with this beautiful set of speakers, panelists is going to be really good to see their ideas on those points. So it says technology is at a strategic inflection point, creating unprecedented opportunity. We are in an era of pervasive intelligence where technology is seamlessly integrated into our lives. Trends are fueling this era. There are trends that are fueling this era. And it says that these trends are increasing design complexity and costs. And then new design paradigms and approaches are essential for the industry to thrive in this rapidly evolving landscape. Now I'll start with Martin again and focusing on key technology trends. Now each of you guys comes from a different industry perspective. So Martin, can you briefly describe what you see as the most significant trends that are shaping engineering today, let's say from the lenses of your industry? And then I'll ask the same question to Danny from the lenses of his industry and to Daniel from the lenses of his industry.
I think before we talk about technology, we've got to understand about the need that's driving the adoption and development of that technology. And I think from our standpoint, from looking at Airbus's largest business unit, which is commercial, the thing that's driving the need is moving us towards sustainability, one of those aspects, while maintaining safety. And what we're trying to do with that is to be able to understand more, to be able to extract more from our products in order to make them more efficient, more sustainable, more manufacturable, for the company itself. And as a result, it's requiring us to be able to investigate more, especially when novel technology comes along. And I'm not talking about technology in terms of modeling and simulation. I'm talking about things like electrification, I'm talking about things like hydrogen-powered aircraft, etc. These type of things, we need to understand their impact, both in terms of their direct impact on the product and in terms of their impact on the industry. And to do this, some of the technologies, and I'm going to come at this from a modeling and simulation standpoint, that we need to be able to employ are the emergence of artificial intelligence and its impact on the design cycle, how we incorporate it, how we make sure that it is safe to use, that it is robust and reliable, that it's explainable. But also more to a physics standpoint, it's about being able to study things from multiple standpoints. Traditionally, we had structures, we had aerodynamics, we had systems, etc. It's not necessarily enough to be able to study those in isolation anymore. We need to understand more about how each one affects the other. So multi-physics and multidisciplinary optimization methods are key enablers towards that sort of more efficient, usable, understandable product in the future, and especially in terms of reducing risk.
Thank you, Martin. Danny?
I suppose I'm kind of representing a perspective from the nuclear industry and partly from defence engineering. I'll talk about the nuclear industry first. We've been seeing a bit of a nuclear renaissance over the last decade and a bit. It's worth observing that the range of different nuclear designs for sources of power, that there was a profusion of them in the white heat of technology era, the 50s and 60s, and you started seeing all sorts of really novel technologies, ways of arranging your plant, materials that hadn't been used before, and all sorts of things being tried. In perhaps ways that a modern regulator might take a somewhat dim view of. They wouldn't stand up to modern safety standards. The regulator would not allow them. But recently, and I think driven by the desire to decarbonize, to generate industrial process heat without having to burn fossil fuels, to provide reliable powers for server farms as well. There is now a greatly increased interest in the use of nuclear power for civil applications, and this has resulted in a lot of the technologies that were initially investigated decades ago being picked up again and being taken more seriously. And you have a number of startup companies aiming to produce small modular reactors or micro reactors to satisfy that growing market demand. So something that, as a highly regulated industry, I've started to see more of is a desire to move away from deterministic analysis to prove the safety of a product. So that by which I mean you'll typically assess worst cases. You'll look at all of your input parameters to an assessment, and you'll set them to a pessimistic value. Yeah, okay, this is what the tolerances would give us, or this is what we think the worst, the extreme bound of a manufacturing process might yield. And you'll combine all of those together, and you'll say, okay, well, we've still got a reserve factor that's greater than the design standard says, or greater than we feel comfortable with. So it's a good design. It may also be quite a conservative design, and the appetite these days is inclining more towards appreciating that there's a spread of probabilities, and that deterministic worst case might occur, once in every however many billion years, and you really needn't be worrying about that. You might be prejudicing your design against penalizing your performance that you can extract from it based on an incorrect view of how likely the failure actually is. So this is moving us towards things like uncertainty qualification, or to an extent probabilistic methods in demonstrating safety, about which we're obviously very cautious, but it's important to be able to extract appropriate performance and to be able to get the most energy out for the the embodied carbon in a plant that you've manufactured. From a military perspective, just briefly, defence engineers in the up until relatively recently might have been pushed more towards improving safety of the product or towards reducing cost. We're not in quite the glade of peace that we were a little while ago, and there is perhaps an expectation that an engineer working in the defence sector might be asked for better performance out of their product, because governments and their militaries can no longer guarantee with quite such a level of confidence that peer-to-peer conflict won't be something that will happen.
Thank you, Daniel. Beautiful. So we'll go to Daniel now. I think so far there have been mentioned a few things that I think Daniel will connect to. So you mentioned decarbonization, sustainability, electrification as part of that, and I think that's very relevant for what Daniel does. And also, as both of you, Martin and Danny, have mentioned, it's also about designing new ways of designs, and I think those are nice things that Daniel probably will connect to.
Yeah. So for the automotive industry, I think two hot topics recently would be one is autopilot. And different companies have different approaches to driving their autopilot systems. Another topic would be the electrification of commercial vehicles. So although I feel that perhaps in maybe around 10 years ago, the main driver would be sustainability, concerns about the environment, but people are starting to realize that actually that depends quite a lot of the energy mix of the country. So electrification doesn't necessarily mean that you have it's good for the environment. And also I feel that we are starting to realize that there are certain limitations in the technology that will perhaps make these products a little bit more challenging to profit from. So I feel that a lot of car companies are now having second thoughts about whether having a full electric lineup is a wise thing to do. I feel that I see that some companies are sort of scaling back, and in the context of thermal management and stuff like that, I feel that obviously electric cars have very different components, and the heat source that generate that has to be managed. They are sort of more concentrated than traditional ICE cars. So we sort of need a new and more advanced we need more efficient heat exchangers, for example, to actually manage to do the thermal management properly, and which is where I feel like Toffee X might be, that's where they come in and provide innovative solutions to our products.
Thank you, Daniel. Maybe I'll stay with you because you so Martin and Danny did as well. While you're mentioning let's say the trends that you're seeing from the lenses of your industry, you all mentioning also a number of challenges, right? And Daniel ended with a challenge, and also let's say you're introducing, let's say, a new concept in this case, which is designing through new tools. And also Martin mentioned at the beginning something related to new modeling systems. So did Danny, a new way of designing. Maybe I'll start with you, Daniel. And what's your take on all of these from the automotive industry? Can you expand a bit on new ways of designing and new tools that can help designing these, and what are the challenges? But the challenges may be related maybe to how you introduce those new tools, how you design using new ways of designing, maybe the different speeds that there are between I don't know, certain technologies that don't progress at the same speed or technology and tools.
So what I see is that like we're still designing, for example, heat exchangers the way we used to design them, from many decades ago. But now we have simulation software to sort of do to help the design cycle, but there hasn't really been any major breakthroughs in the design process itself. And like I feel that like some of the heat exchanger products that we can buy off the shelf, they don't actually provide enough capacity to meet the new generation of electrical vehicles. So and that limits how we can design the rest of the system. So we won't. So for example, like the chip size might be limited because we cannot dissipate heat quick enough for us to size them down any further. So that sort of using traditional ways to design components put a limit on how we design like future generations of our vehicles.
Thank you, Daniel. Martin, what about from your perspective? I think that it might be a little bit different for you, but there might be some connections.
I think there are probably three things that we're facing as significant challenges in engineering at the moment. I think one is something that Danny touched on earlier, which is the application of regulation into the design process. At the moment, we treat them as hard constraints. And some of those constraints that are applied by regulators were designed quite a long time ago. But as our products become more complex, and those regulations were written for single disciplines and single regulations, actually understanding how they affect multiple different disciplines starts to become complex. You start to introduce additional variables, additional complexity that you need to be able to study in order to understand where they're tapping into one another. And I think we also need to be able to understand where we should maybe try and push back against regulation, not to compromise safety, but to say that we understand this better, or we have a new simulation method that allows us to better explain what's happening over the product's life cycle that should allow us to relax those constraints. But we don't want to do that ubiquitously. We want to be able to accurately target which ones are having the greatest effect. And that's about understanding. I think the next aspect is about the scope of the problem. So us, like automotive, like submarines, we've developed iterations of the same product for quite a long time. And now we're in a situation where there are new technologies for design, there are new materials for application, etc. And trying to understand how much of an impact those new things can have starts to create even more complexity into an already complex situation. And this sort of puts us towards where we're using TOFIX and we're using other software like this, which is there are three stages of design. There's concept, preliminary, and critical design. 80% of decisions are made during concept design, but in concept design, you need to be able to explore, but you need to have faith in what you see from your simulations, that your design decisions that you're making in that concept design phase are worthwhile and worthy of investigation, because those designs that you pick are then going to go into your next stages, and going down the wrong avenue can lead to substantial amounts of loss for the company in terms of time and money. And so I think being able to bring new methods, technologies, etc., into that concept design phase, but actually exploring a reasonable amount of scope around some of the aspects that we don't traditionally necessarily include in a big multidisciplinary scenario, would allow us to make potentially better design decisions in these early phases, which can then be utilized in order to drive our reductions in time, if you will, over our preliminary and critical design phases as we've got more confidence in them.
Thank you, Martin. Daniel, I think this is serving a good ball to you, especially the points of say regulations, new tools, especially at the very start of the design, as Martin is mentioning, and perhaps related also to performance, which you mentioned seem to be a key thing that is resurfacing especially in defense.
It's serving several good balls, and I'm trying to decide which one to attend
Go
to
for
first.
All of them.
Well, yes, the point about increasing the increasing complexity, the increasing multidisciplinary integration that's required. That I find that comes as well from I suppose ever escalating customer expectations and aspirations. We want the component to perform its function better, or we want the component to perform multiple functions within the same volume or the same mass. And this as well as which the ever-present digital trend that you may be required to integrate sensors into regions that previously you'd leave as a dumb block of metal. And then, so a designer now has to consider a rather broader range than perhaps they used to, and they're always trying to extract more performance or the same performance for a reduced cost, and all of this means that they have more different either different engineering disciplines to bear in mind, different physics to model at the same time, or more integration between their own and different departments, and heaven knows that the multidisciplinary integration is very hard. We do a lot of it, so from right from the quite abstract through to down on the shop floor, trying to make sure that all of the engineering disciplines know what's happening and know what the other teams need, understand their appetites and their limitations, and that complexity adds a lot of difficulty to the design process, and time and cost if it's not done well. I will pick up on regulation briefly. It's a good example. I know that some of my colleagues in Rolls-Royce Submarines have been trying to get some external standards changed to reflect that some components could be additively manufactured. The design standard doesn't necessarily accommodate that very well, and doesn't give you a good way to prove that your design is good. So you end up having to do it very much more from scratch. I think that the one other thing I'd like to bring up is that with exciting new digital tools turning up all the time, thank you Toffee X, but you have this is a sort of emblem of having more computational resource at your disposal during design. This has been a trend for as long as there's been an industrial revolution, but this means that firstly you have more data to sift, whether it's during the design phase, whether it's sifting in service data. I'm sure that Daniel and Martin have more of a problem with that because they have more platforms than I have to worry about by a long chalk. But also you have to decide how you're going to interpret that data, the data that you get during the design phase, and it's increasing in volume. You need to understand how to treat it. Nevertheless, you still have to crystallize this into one design, and you've only got a certain amount of raw evidence from rig testing, from past operation. Some of the rig testing is expensive and time consuming and takes in some cases decades because you need to observe long life effects, and all of this means that the quantity of information that you have to integrate during the design process can be, on the one hand, it's steaming ahead at an enormous rate while these digital tools are developing, and at the other, it's still stuck on the stuff that you happen to know from some measurements that you took in the 80s. And that disparity is very difficult to manage. You end up with much more uncertainty in some parts of the design process, in some of the inputs to the design process than from others.
Thank you, Danny. Daniel, yes. I believe some of the things that Danny and Martin have said might resonate with the automotive industry. I'd like, if possible, if you could focus maybe on a few things like Danny mentioned additive manufacturing, for instance. He mentioned new way of designing. He mentioned also now in his last words, effectively a few challenges, but also the length length of the design cycle. And I wonder if you can comment on these. And also, I remember when we chat last day, you mentioned something which is, yes, there is an element which is related to the way we design, and maybe we need to address that and perhaps evolve that. But there is also the human factor, I think you called it, which might be different. I mean, in automotive might be different than defense and aerospace.
So I feel like traditionally we design components, relying quite a lot on the engineers' creativity and engineering knowledge and experience, and then we do like a validation using some sort of simulation tool, and then we go back to maybe improving our initial design, and we go through that cycle a few times. Knowing how to design a part that can be manufactured is an engineering know-how. But with additive manufacturing, I feel like the situation sort of shifts a little bit towards performance focus, because now we can actually manufacture these shapes that we previously couldn't manufacture. So there's we also need a process that can efficiently generate these shapes that will then be additive manufactured, and these shapes are beyond what like a normal engineer can comprehend. So we need tools that can do, for example, topology optimization. And so like the design process now sort of becomes interpreting an engineering problem, translating that into a physical problem, and then selecting the correct tools that solve the physical problem as a mathematical model, extracting the result back into a physical solution, and then based on that solution, create your own engineering solution. So I feel that like the flow of how we design things have shifted, if you know what I mean. And also like another challenge other than like regulations, like for the automotive industry, there isn't a very clear guideline as to how we can use additive manufacturing. So on the regulation side, I think it's quite ambiguous. And then another factor that is sort of pushing back the application of additive manufacturing parts is something that I mentioned with Lucas, is like human factor. A lot of the engineers in our company, they're not too familiar with the technology, and they're more comfortable designing things that, the way that they have always designed things. So I feel that like sometimes it takes a lot of convincing for people to even try to have to include an additive manufacturing component in their system. And at the moment, the scale and the cost makes it impossible to replace an entire system. So it's more realistic to replace perhaps a part of an existing component. So we sort of need the help of engineers from other departments to actually allow us to work alongside them and demonstrate the usefulness of additive manufactured part within the system that they are designing.
Thank you, Daniel. I let Danny or Martin jump in if they want to make a comment.
I'd like to, if that's all right. The point you made, Daniel, about perhaps a reticence for the adoption of additive techniques is something that, again, rather conservative industry I've certainly observed, and you can end up with, I suppose, a need for, I won't say cheerleaders necessarily. I don't actually have a set of pom-poms that I use at work, but you have to try to provoke people into creativity sometimes. Excellent professional engineers, but nevertheless, if people have been used to conventional geometry and conventional manufacturing techniques for a long time, then something to help them see the advantages of doing things in a different way, a different layout or a different manufacture technique can be necessary, and that might be a set of really juicy analytical results suggesting a big improvement in performance, or that might be a little physical model. But one way or another, you've got to capture people's imagination in order to try to get this the sort of change that we're talking about today, to realise the future of engineering design.
Thank you, Danny. Martin?
I think what Danny mentioned about additive manufacturing is probably quite true across most modeling and simulation tools as well, in that people have a way of doing things, and when they're introduced to a new tool, they're often very busy with the day job that they have to do, and they have a choice as to whether to try and upskill and use the new tool, or they just get on with it the way that they know and have something that they know is going to have a fixed workflow and they'll have an output at the end of it. I think making time with engineers within their working cycle to actually upskill and embrace new tools, having internal training sessions and mentors that allow people to pick up new tools quickly is really, really important to getting through the change curve, and allow people to start exploring what these new tools can offer them. And I think the same is true for additive manufacturing as well, and being able to demonstrate, as Danny mentioned, with your pom-poms, etc., to be able to actually showcase how this offers an advantage to you is really important in getting us towards the embracing of new tools and new methods.
Thank you, Martin. I'll start with you if that's okay. You're also associated to university, so you've been in the industry for many years. You have seen this evolution of engineering design, let's say from probably when you were a student to your profession to maybe talking to students. Mm-hmm. Can you just make I would say, speculative comment on this evolution, a bit a light comment on this evolution, and maybe how you see generative design helping as we move forward, and if you look into 2050, what do you see an engineer doing? And then I'll pass this over to Danny and Daniel for let's say, so you guys start thinking about 2050. What do you see in 2050?
I think in terms of students and youth, I think their ability to pick up new methods quickly, easily, without risk, etc., I think is really empowering. And I think the ability to do that during your undergraduate degree into your placements and into the first years in work is really, really useful, not just for themselves, but for those around you as well. We have a great amount of cross-fertilization from our various students as they come in and work alongside us. And I think what we try to do from a central research and technology point of view is determine which of these methods might have substantial impact, and work with our universities and with our undergraduates and with our PhDs in order to develop these methods and skills, and then bring them along with us into the company and then transfer them into the business unit as technology leaders, so that they can accelerate the technology and its adoption into the business. I think in terms of as we move towards 2050, I think even just now, in terms of what people should be looking at and what differences we see, I think the sector or the sectors across all of us are more open than they probably were. We used to have automotive, aerospace, etc., and there was only limited sort of crossover between the two. But now, in terms of the modeling and simulation techniques, there's always been some crossover. But now, in terms of the technologies, electrification, etc., thermal management, etc., all of these are starting to transfer across. But additionally, you start to see some parallels in the medical and biological industry in terms of how they simulate and do things, and how that has effect on how we study battery chemistry and how we study porosity, etc. All of those things now mean that you have to have well, you don't have to, but you can have a much more broader awareness of what's going on, and that can really help you to determine where the correct path should be. I think as we go towards 2050, I suppose the biggest change we'll probably see, or I think we'll see, is that AI will no longer be a thing that you start to think about and how it's applied. It will be as ubiquitously applied to engineering principles as Microsoft Office is to your general day job. or equivalent tools are available. But in terms of what you're actually going to be doing, these will be commonplace applications using neural networks and surrogate modeling methods, etc., as part of your design process. Will be not necessarily uniform, but it will be done quite commonly. And I think it's about how we prepare the future for that, for the application of these techniques across our industries.
Thank you, Martin. Danny? 2050 then.
Moving towards 2050, I'll start a little closer to home, if closer to the present day, if I may. Something that we've been kicking around as an idea in Rolls-Royce Subs is the distinction between a design tool and a substantiation tool. A design tool is something you'd use to explore potential concepts, to try to understand your design space in more detail, to sample around a really broad range. And it doesn't necessarily matter if it's accurate, and you know you're going to have to do something with the information afterwards. But it can be very illuminating. Generative design has been quite useful for that. The substantiation tool is what you would present in front of a regulator to demonstrate this is safe and here is the proof of it. And at the moment, I don't see that being where generative design tools are. There are too many other things to reflect to the degradation mechanisms, fouling, through life distortion, things that it's really hard computationally to model in an optimization where you're doing thousands of iterations. That may change in the future. It may. I would expect that as computational power increases, potentially we'll see where quantum computing goes as a way to potentially enable that. But it's going to be feasible to include more within the scope of an optimization, to ask a more sophisticated problem and get an answer that reflects more of the phenomena that you might wish to understand for what the product will actually see. So I think that we would expect that modern tools will become more capable of representing the circumstances that really the designers are interested in. This tends to provoke more manufacturing development, more methods development, because if you have come out with this interesting novel geometry and you take it along to somebody on the shop floor and they say, well, I can't do that on a lathe, then you need to do something else. If you really want to realize that design, then your manufacture process has to come along with you. You may have to develop a process and material combination that nobody else is using at the moment, in order that you can actually realize these wonderful intricate new designs that you've come up with that look like ants' nests or leaves or what have you. But I'll fix on for the view to 2050. I'll fix on the shop floor to start off with. In training area where our many apprentices get some basic workshop skills, you have rows and rows of lathes and mills and welding booths and so forth, and people will use those. You will have a person standing at a machine and paying attention to it, and that's not really what happens in a modern factory anymore. You have CNC machines that will actually do the work, and someone will check them and will set them up extremely carefully and will pay a great deal of attention, but then will walk away and will go on and do something else that's productive. And with the trend has continued, and now in some of the most advanced factories, they're dark factories. You don't really have any people in them most of the time. In fact, you don't really want people in them most of the time, because they'll only change the input variables and spoil the product that you get. I'm wondering about whether in the future it's going to be a trend towards not just dark factories, but dark design offices, where you've got very sophisticated tools that you need somebody, or perhaps in the future something that will critically assess the output, will direct them, will help them to these tools to all interpret requirements in a direction towards a finished product. But more of it is automated. You don't have people using slide rules anymore. You might not have people running analyses anymore. That might be something that the computers do. Which leads you to wonder what the person who's applying the critical judgment is actually adding to the process. If you can train all of these systems to do those activities to do with analysis, to do with providing evidence, then can you also train a system that will be able to assemble this into a coherent safety case and demonstration that you meet your requirements? That I think is the challenge. The challenge I'll sort of pose there is that how do you train a person to be competent to do that when they haven't spent the time, I suppose, putting the hours in running assessments themselves? That running the assessments is part of how you gain experience and expertise, and that enables you to make judgments about whether output is good, or what its failings might be. And if ordinarily that's being done by sophisticated digital tools instead of by people. You need attention on how you're going to develop people to be capable of exercising that judgment when they see those results.
I'd say that's very, very good comments. Also fascinating, some of the things you say. Daniel.
After you asked me that question a few days ago, I went back home in my 25-year-old car, and it still looks, actually it still drives very well, and it's still relevant today. So I was just thinking, in 25 years, are the cars going to be very different from the cars that we have now? And I think ultimately, what we can design is, well, it goes hand in hand with what we can actually manufacture at a reasonable cost. So, and for example, like now we have like giga cars or other manufacturing methods that are sort of changing the way we think about component design. Additive manufacturing is another technology that might have an impact in how we design our products, but I feel that there are, major roadblocks at the moment, especially with the cost side of things that are sort of limiting the application of the technology. So, fast forward to 2050, if there are major breakthroughs in perhaps energy or laser technology or other sort of auxiliary technologies that support that are essential to additive manufacturing, we might see products that look very different from the cars that we have now. Another aspect is that I feel that like cars are essentially, they address the needs of mobility, and the needs might change very significantly, especially with the with like virtual reality and stuff. Like people might not actually need to move, that much anymore. It might make more sense to just put on your VR goggles and work from home than actually, commuting to work. If the quality of VR is so high that it doesn't actually make any difference. So I feel that like there might also be a shift in what people want in 2050. Maybe there will be two extremes, like cars that they just do they just like help people commute. So maybe like automated autopilot like Uber, that they're not they're shared. So perhaps the design isn't really that isn't too important. There doesn't have to be too much styling or character to those products. And then on the other extreme, maybe like people still want to own a car. It might be similar to how people still want to own a horse. Like learning how to drive might be similar to learning how to ride a horse. And those people will want to customize their cars a lot. So that's perhaps where additive manufacturing can be applied quite effectively and have, cars that are highly customized, and perhaps those cars will become almost like a luxurious a product rather than just a pure means of transportation.
Beautiful. Thank you, Daniel. So we're almost on top of the hour. I wanted to leave a couple of minutes for the audience to ask questions. But before we close, I have a question for all of you. If you could give just one piece of advice to engineers preparing for the future of design, what would that be? You can go randomly, whoever wants to go first.
I'll jump in. Stay grounded in the engineering fundamentals. It's wonderfully exciting when you have a new tool and it gives you new ideas, and yeah, great, this is gonna quadruple the performance that we get out of this component or system. It's really important that you're able to interrogate that and say, right, okay, it's nice, this geometry, it looks, the numbers look good. What are the phenomena that are happening here? Is anything about the change from the designs that we know and presumably love, is that are the changes something that we can explain in terms of, yes, I studied that at university, I can see that that's nuclear boiling that's happening there, and that means that the new feature is a good one, or is it just a mystery? There's you might have heard of the Rickover principles. We like them in nuclear engineering, but one of them is, if you can't write it down, then you don't understand it, and if you can't explain why your design is working, then it's not a design, it's a liability.
Great. Daniel or Martin? And I'll have a comment for that, Daniel, later. I like that.
From my point of view, I've never seen a period with such a dynamic shift in what potentially will come next. In my 20+ years in aerospace, we have this huge change in terms of aircraft architecture. We have a huge destabilization of the world in terms of geopolitics. We have a change in how people move around and interact with one another, all coming together to change exactly how a product fits into the marketplace. And I think this presents a great amount of opportunity, not just in terms of the direct engineering, but actually studying the things that enable that engineering, which is the science that underpins it and the mathematics, but also something that Daniel touched on earlier, which was that everything has a price. So you need to study it in the context of the business, in terms of how it actually fits into the business, whether it's worthwhile investigating that technology and what it will do for the company, for the product, and then how you unlock it. I think keeping that awareness is as critical as keeping the grounding as well.
Thank you, Martin. Daniel.
I was going to say something quite similar to what Danny just said. I think the temptation is that with all these new tools, it's very tempting to, solve a simple problem with a very high-tech solution. I think the elegance of engineering is to solve a complex problem with a solution that's as simple as possible. And I feel that people should bear that in mind as these new tools keep coming up.
Thank you, Daniel. If I can close with a final comment before taking questions, I do like what you guys have brought up in this panel today. I think we could keep on talking for the next probably 10 hours. From my side, I wanted to add a comment on the business side of things. I think what Martin brought up right now is very important, and I'm talking as an engineer whose initial career was just about technical stuff, and then I realized, okay, wait a minute, I need to have a little bit more business sense in what I'm doing. And the other one is maybe I'm mispronouncing this with the Italian accent, but explainability. I hope I'm pronouncing this correctly. Explainability of results, and that's one thing I must admit we want to do in TOEFL. We don't want absolutely to provide tools that are black box, and that might be we might be lucky, because the beauty perhaps of topology optimization for thermal fluid applications is that you can actually try to interpret the results, because it's the physics that is telling you something. So as long as you have spent your time in university or during your engineering career in understanding how physics, engineering, mathematics works, you should be able, with a little bit of thinking, to understand what in this case this tool is telling you. Okay, and take this as an inspiration to design maybe the next generation of products, and hopefully, as Daniel says, in an elegant way, maybe bringing some solving some of the complexity of engineering with solutions that may look complex, but in the end are simple, because that's what nature is telling us, right? And that might be a little bit different than some AI tools where you actually plug in a lot of numbers and then you get out something and you have no idea why. I think that's a bit of a difference.